To briefly review the idea of cross products, remember that there's two types of operations you can do on vectors that are similar to multiplication but very different. The dot product, which is also called the scalar product, takes two vectors, multiplies together their magnitude, and then cosine of the angle between them. So theta is just the angle between these two vectors. This fundamentally creates a scalar. It does not create a vector. The cross product does something similar where you have a and b, the magnitudes of the vectors, now sine of the angle between them, but you have a new direction that comes out. And we would say that that's given by the right-hand rule. Note that this is fundamentally creating a vector. So this is one reason to be really careful with your notation and make it clear when you're referring to vectors versus their magnitudes, and be careful about just using multiplication symbols, where if you write something like this and what you actually mean is just multiply together the magnitudes of each of these vectors, it's really quite wrong to write it as A cross B if you don't mean cross product. So be very careful about your notation. Remember that these two slightly different things. Dot product goes with cosine, cross product goes with sine, but from cross product you must get a new direction. So I'm not going to get into the details of the right-hand rule in this video. There are other videos that do that. But I want to remind you some basic properties of the cross product that will help us thinking about the magnetic field direction from point charges. So when you have the cross product of two vectors, these two vectors always lie in a plane. Now that might not be as simple as the x plane, like the xy plane or the yz plane, but you can always connect two vectors together with a plane. Their cross product is perpendicular to that plane, and the magnitude is given by the magnitude of each of these vectors multiplied by sine of the angle between them. The book here is using alpha for the angle between them, where before I was using theta. But note that it is perpendicular to the plane that they make, and that's usually going to be enough information to figure it out, as long as you're then careful about does it go up or does it go down. And that's where you can use your right-hand rule. So if we say that this is C cross D, it could have either pointed straight up or it could have pointed straight down. The way that I think about this is you start with your hand kind of making a flat palm, and you point your fingers towards the first vector, in this case C, and then you start your fingers curling towards D. Notice at this point, if you put your thumb out, your thumb points straight up. The reason that's interesting is because you can say, well, what happens if you do D cross C? So if you do D cross C, again, it must be perpendicular to the plane between them. You start with your hand pointed towards D, but you actually have to turn your hand over if you want to curl your fingers towards C. At that point, your thumb points down. So this vector is actually D cross C. Opposite in direction, equal in magnitude. So now let's think about our Biot-Savart situation. So same picture as before. Note that there's a plane here, this up-down plane, that R and V both lie in. So because R and V both lie in this plane, we know that our magnetic field vector must either be directly to the left or directly to the right, because it's perpendicular to this up-down plane. When I say left or right in this case, I mean from the point of view of the charge. So we would do V cross R hat. So again, starting with your hand kind of pointing in the direction of V. The only way you can curl your fingers slightly in the R direction, so curl them slightly up, is if your thumb ends up pointing to the right. So that's the idea here. V cross R gives us a direction, again, that's rightish here with respect to this point charge. So here's a really simple example. You have a charge here, and there's a dot. And the question is, which direction does the magnetic field point to the dot? Or is the magnetic field zero there? Now again, keep in mind that this needs to be fundamentally a three-dimensional problem. So this could be a multiple choice problem where I say up, down, left, right, into the page, out of the page, but you also want to make sure that you rule out magnetic field just being zero at that point. So note that your velocity vector has already been given and your r hat vector has been given, and that's just showing you that your r vector is this way. So what do we do to actually think through this and figure out the answer? Well, remember the formula for Biot-Savart? The reason you use that is you're getting that V cross R. That tells you the direction. So you start with V and then curl your fingers towards R. First thing you want to do is rule out 0. So because our charge is moving, that's good. At least some points in space have magnetic field. Remember that we said all of the points directly in front of it and directly behind it had 0 magnetic field. Now for our part of our points, it's not on that line, so it's not 0. Now, something to be careful about is this charge appears here, and in this case our charge is negative. So what I recommend you do is first calculate V cross R and keep in mind that that's the direction for a positive charge. If this is, for instance, an electron, our charge is equals to negative E. So when we do the right-hand rule for V cross R, I start with my hand pointed along V and I curl my fingers down towards R hat. My thumb then points into the page. But I don't have a positive charge, I have a negative charge. So all you do is flip that around. Instead of into the page, it's now out of the page or out of the screen. So hopefully this logic makes sense. I now want to see if you can do it on your own. And again, keep in mind that you should expect to see a question like this on the TBL. So you're not really using the values in this equation, but you do need to know that it's V cross R and not the other way around. So in this case, we have a dot, we have a positive point charge, and velocity is out of the page. So again, the charge is coming basically straight at us. So I'm going to pause the video. You should pause it for as long as you need to think about this. Pick the direction and decide, or is it 0 there? Okay, hopefully you've paused and thought about this. So again, we want to think about V cross R hat, just to give us the direction. And our hat is going to point towards that dot. Now V is out of the page, so this is a little bit tricky to do, and I find that some students aren't willing to really commit to turning their hands the way they need to, and so they don't really do this. But you can basically turn your body away from the screen and then point your hand away from the screen. If you keep your body towards the screen, this is much harder to do. So if you point your body away from the screen, and again point your fingers away, you then have to orient your hand so that you can curl your fingers towards the left direction, the direction of our hat. And at that point, my thumb is pointing down. So V cross R gives you down. Now, because we have a point charge, that's all we need to think about. And so we get to say that our magnetic field direction at that point is going down. And again, remember that you can also just use the right-hand rule. We expect this to be circles. And if you point your thumb in the direction it's traveling for a positive charge, we expect the whole circle to be going that way. So that's also consistent.